Function calling is one of the most powerful tools that you can use with your language models. By training and using models that are able to provide structured responses, you can then send those responses to an arbitrary API. This means you can connect a model with basically any other service and use structured Python code or any code to send and receive data. In this video, I'm going to go through using function calling datasets to fine-tune models. I'll go through quite quickly the fine-tuning of models for function calling, and then I'm going to focus on inferencing function calling models. There is quite a bit of setup if you want to use function calling because you have to provide data on the functions that you want the model to be able to use. And when the model responds with a structured response, you have to be very careful in how you handle that response and properly send it to make the function call and return the information that the model needs. Here's what we have for agenda. I'll start off by introducing what a function calling model is, giving you Llama 2 as an example. I'll show you the repository, which is open and available for you to use. Next, I'll show you a function calling dataset that I have developed. It can be used for training any model to be able to do function calling. And it's the dataset that I use for any of the out-of-the-box function calling models that we'll talk about during this video. Next up, I'll quickly go through fine-tuning models for function calling. This is something I've covered in quite a bit of detail in a previous video. I'll just show it up here. But let me give some latest learnings that I have on fine-tuning. The focus of this video will then be inferencing. I'm going to talk in detail about how to send function data to models, how to get back function calls, handle those function calls, and send back the responses to the model in a way that will be useful for them. I'm going to go through a few examples here. I'll actually very quickly run an OpenAI example of function calling, but then I'll focus on custom models. I'll do Llama 2, I'll do OpenChat 3.5, and then I'll do DeepSeek Coder, which is a 67 billion model. These models are all available out of the box on Trellis Research Repo on Hugging Face. Just look up huggingface.co/Trellis and you'll find the models. There's also a Yi34B with 200k context model available for function calling. Oh, by the way, we are going to have a few extras as well. I have been asked to test out the model en español. Probamos en español si podemos hacer los function calls. I'll do a little bit then on highlighting how to decide which model you should use, what size model you should use if you expect different performance, and I'll finish off with a few final tips. Let's start things off here on huggingface.co/Trellis. You can scroll down and you can take a look at the collections. So let's just expand the collections here and take a look at function calling v3. Note that this is now going to take precedence over function calling v2. So if you're going to use models, you're probably better off using v3. The main difference being that they use the OpenAI format for function calls. That doesn't mean the data was created with OpenAI. I've created the data myself manually so that there aren't licensing issues. But the format of the metadata is the same as OpenAI, which makes it a lot easier if you're already doing function calling with OpenAI. Let's head into this collection here, and you can see that there are currently 5 models. There's OpenChat, there's Mistral, Llama 2 7B, Yi34B, and then DeepSeek 67B. And we're going to start off with the Llama 2 7B, which is publicly open for you to try out. Now, as I said, I'd start off just by explaining what is a function calling model. Well, it's a fine-tuned model of some base model. In this case, the base model being Llama 2, specifically the chat version of Llama 2, and specifically the 7 billion parameter model. So it's the smallest Llama model from Meta. To understand what function calling is, it's easiest if you take a look at an example. So I'm going to scroll down and we can take a look here at a prompt. So the idea with function calling is right at the start of your prompt, you tell the model that it has access to certain functions and to use them if required. So here I've provided 2 functions, getBigStock, which is to get the names of the largest N stocks. And the next function I've provided is getStockPrice. So you put in the name of a stock and it should return the price of the stock. So of course, a language model is not going to know the current price of, say, Apple stock because the price moves around. So the idea is if you have an API that can give you the price of Apple stock, well, the model can tell you by doing a function call, hey, I want the price of Apple stock. And then you can get that from the API and send it back again to the model. So you'll see just a few things here. For example, to get the stock, the model will need to provide an array of the stock names. And I'm saying that's a required parameter. So if the model calls to get the price of a stock, it definitely needs to give the names of the stock. It can't just say, give me the stock's name. It needs to give the name of the stock. All right, so after that prelude where we tell the model what functions are available, we then ask the model to get the names of the 5 largest stocks in the US by market cap. And then we have this token, which is typical for Llama, that indicates the end of our instruction. So we would basically send all of this prompt, everything up to this point here, to the LLM and get it to respond. And if the model is fine-tuned for function calling, it will respond with a structured response like this, which is a JSON object that gives the name of the function to call, which is get big stocks. It gives then the arguments, so the number of big stocks to find the names for, and also the region, because that was a parameter we said was possible within the function details up above. And then, because Llama uses /s for an end of sequence token, it emits this token to tell us, okay, I'm done. I've made my function call, so get me that information, and then we can continue. So this is a function calling fine-tuned model. If you did not fine-tune the model for this purpose, then you would get a much different and much crazier response here. We'll actually see some examples of that during training, because I'll show you what it looks like to try and do function calling with a small base model, and I'll show you the difference between before and after. Now that you know a little bit about what a function calling model is, let's answer the question of how you would train a model for function calling. Well, as with any training, you need a data set. Specifically, you need a data set that has function calls along with the responses, so you can habituate the model to responding with the structured JSON response. And you'll see linked here, there's the data set that I use for fine-tuning, and it's available on Hugging Face for purchase. If you take a look at it, it's quite a small data set, 66 rows of training, that's the data used to train, then 19 rows for validation. This is to calculate an independent loss during the training. So you check that the model is improving without overfitting. And then there are also 7 test rows. These are some test examples where I use totally different functions just to see how well the model is performing on a quite independent data set. Now, the reason you don't need that much data is you can read the Llama paper, less is more. Actually, for fine-tuning, it's more important to have very high quality examples that you send into the model rather than having a large amount of low quality samples. So that's how this data set is focused. As I mentioned earlier in the video, it was created manually by me. It was not created using ChatGPT or other models that have more restrictive licenses, and therefore you can use this for commercial purposes. So let's just take a look at some of these prompts, and I'll very briefly describe the data structure. Let's start here down in the middle. So we have 3 sections, 3 columns. We have the function list. So it's just a list of functions like I previously showed. Then we have the user prompt, and then we have the assistant response. So here, for example, we have 2 functions. One is search archive, which is for patents, and the other one is get the current weather. So the question I then ask is, I'm going on holidays later today. How's the weather in Boston? Give me the temperature in Fahrenheit. And then the response is name, get current weather, arguments, location, Boston, USA, and the unit is Fahrenheit. So this here is the function call. And the whole idea is we're going to feed in the left 2 columns as part of a prompt, and then we're going to have the model generate a response, and we're going to compare that response to the assistant's response here. And when there are differences between what the model is predicting for the assistant response and what we would like it to be, we penalize the model and backpropagate so that the next time the model will be a little bit closer to giving us this structured response. Now, just a few little comments. I'm going to get into some specifics here, some little comments on why certain data is included here. You'll see this is quite straightforwardly just a function call. But you might have noticed right up towards the top, I have a question here that has no function call at all. It says, what happens to you if you eat watermelon seeds? And the answer is watermelon seeds pass through your digestive system. This is taken from the truthful QA dataset. And the reason I include this is because I want to get the model used to seeing functions in at the very start. but then responding normally to a normal question. Because what I don't want is, if I put a lot of functions into the model at the start, I don't want it to just keep responding with function calls, even if I ask a trivial question. Well, I don't know if that's trivial, fairly trivial. What happens to you if you eat watermelon seeds? And then just a few other examples down here. I also have put in some pretty kind of nonsensical or single word prompts like pair of scissors or typewriter. And then I get some response here. And the reason for this is sometimes if you just put in a single word in a prompt and you have function list beforehand, the model thinks it wants some kind of a function call on that single word. But really, the user shouldn't be putting in just single words. And if they do, then you really want to either respond in some sensible way to that word, or you might want to ask for further context. Let me see if I can find an example here. So if I just prompt a model with some functions and then say why, the answer I would like is, could you please provide some more context or clarify your question? I don't want a function call with why. So that's a very brief overview of this data set here. It's built on 8 base functions, and I use different functions then for the test set, which you'll see when we go through the training, so we can have an evaluation of that. And indeed, I have pre-trained some models. So if you want to get some pre-trained models, you can just check out the Llama model that I've already gone through here. Or if you'd like, you can purchase any of these pre-trained models here if you want larger, higher performing models. Or you can even purchase the data set here, V3. Next step is to train these models using the dataset for function calling. There is a handy resource here, trellis.com/function-calling, where you can see a list of the dataset, the pre-trained models, but also you can find a link to the training notebook that I'm going to use right now. You can purchase the script by itself, or you can buy access to the advanced fine-tuning repo, which has a lot of other scripts, including for supervised, unsupervised fine-tuning, direct preference optimization. Also, there are scripts for quantization for GGUF and also for AWQ there too. So I'm going to go over and use RunPod. RunPod is a cloud server service, and it allows you to quickly deploy a GPU. You could, of course, use your own GPU if you have one. You could also train on a Mac using your Mac chip if you have an M1 or M2. There are some tips in the advanced fine-tuning repo for that, although I hope to dig in and do more of a series later. Anyway, let's get started here on RunPod. I'm going to go to Secure Cloud, and you can find Trellis referral link if you want to support the channel. You can find it below in the description. So once you've created an account and you've topped it up with some money, you can deploy. Now, I like deploying the A6000. It's got 48 gigabytes of RAM, so it's good for training 7B models, 13B models in full precision. You can also train quantized versions of 70B or 34B models as well. So let's click on deploy here. I'm going to go through an example for Llama 7B. So when I click on customize here, I don't actually need that much space. That's probably more than enough. I can just put in 50 here. Now, actually, I have used the wrong template here. So I'm going to go back. I'm going to go to deploy. And the template I want for training is not an inference template. I want the RunPod PyTorch 2.1. So a PyTorch. And here, I do like to increase this a little bit. The 7B models are about 13 gigabytes in size, but you end up needing to save them a few times. So I recommend leaving some headroom here, and you can set overrides, continue and deploy. And it'll just take a few minutes for this pod to start up. And once it does, I'm going to run a Jupyter notebook on this pod and upload a script, the script I mentioned from the Trellis homepage here, or the advanced fine-tuning repo. All right, the pod has just started up. So I'm going to click on connect, and I'll connect to Jupyter Lab here. Once Jupyter Lab opens up, I will upload my function calling v3 script for training. By the way, you can do this in Google Colab as well if you'd like. I think that is fine as an approach. If you want to use the T4, you can also pay and use a V100 or an A100. The A100s are small on Collab. They're 40 gigabytes instead of 80. So it's actually smaller than an A6000, and I think it's not actually cheaper. So I like training with the A6000. It also allows you to use Flash Attention version 2, which allows you to speed up your training process. That's not possible if you use a T4 because it uses an older architecture. All right, so I'm going to upload my file for fine-tuning. Okay, I've uploaded a fine-tuning script. I've also uploaded a quantization script, which I'll briefly talk about later. But let's get started with this fine-tuning script. And the first thing you want to do is you want to log in with Hugging Face. The reason is so that you can push the model to Hugging Face later on. Or if you're using a gated base model, then you need to be logged in so you can access it. After that, you can set your base model. Actually here, I'm using OpenChat. I think that's fine. We can go ahead with OpenChat. And next, I'm going to do some installation. You can see I'm installing transformers, Flash Attention. If you want to fine-tune a quantized version, you can install bits and bytes and accelerate as well. So after some imports, we're then going to load the model. Here you can see I've commented out quantization config. Let me just increase the size of my screen here. That's going to help a little bit. So here I've commented out quantization because I'm going to train with full precision, or rather BF16 16-bit. That's how I have fine-tuned all of the out-of-the-box models. I just think it's slightly better for quality, but generally it's probably fine to use bits and bytes quantization. The quality is reasonably good, although there can be some complexities in pushing it to hub, which I might get into on another video. All right, I'm using Flash Attention 2. You can't use that unless you're using either an A100 or H100 or an A6000, maybe some other architectures, but you can't use it on a T4, so just be careful about that. Once the model is loaded, you're going to set up the tokenizer. And once I've set up the tokenizer, I like to check what the end of sequence token is. For this model, it's end of turn. And what the pad token is. There's no pad token specified for this OpenChat model. I set the tokenizer padding to the right-hand side when I do function calling. I think that's good for short responses because I like to have the model start off. It'll start off with the prompt and then give the response and then the padding, rather than have a lot of padding before the prompt and the response. Okay, so since there isn't a pad token already specified, what I do is I need to set a pad token. If there's an UNC, which is an unknown token in the tokenizer, so this represents any unknown tokens, I like to use that. I generally don't like adding a new pad token if I can use something already in the tokenizer, because adding a new pad token means that there needs to be a new token added to the tokenizer, which means that people need to use your new tokenizer with that token added. It just adds an extra piece where things could go wrong. So in this case, the UNC token is in the tokenizer, which means that I can use it. So I set the pad token to be equal to UNC. And I don't need to change the number of tokens in the tokenizer. You can actually see there's 32,002 tokens. Generally, the number would be 32,000, but 2 more special tokens have been added, in this case, by the model creators. You can actually see here a list of the special tokens. They've added in these end of turn and pad 0 tokens. Okay, so then I'm going to print out the model architecture. OpenChat actually uses a Mistral type architecture. And next, I just print out a sample string and tokenize it. The next step here is to set up LoRa. So rather than fine-tuning every single parameter in the model, we're going to fine-tune only certain parameters in the model, so only certain modules. And we're not going to directly fine-tune those modules. We're going to fine-tune an adapter, which is a smaller representation. So if you imagine a big matrix to be trained, what we do is we say, okay, we're going to train a smaller matrix, and that smaller matrix will have a mapping onto the larger matrix. And we're going to freeze all of these parameters in the main model and just train this adapter. And at the end of the training, we're going to expand this adapter up and merge the 2 weights, the fixed weights and the training adapter. So this is called LoRa. It's low rank because this matrix here has got a low rank. You can think of it as a low number of rows or columns. And this ends up being more efficient for training. And it also turns out that the performance is very good. The reason being that large matrices within language models actually could be represented with lower rank representations. So this means actually you don't need to train something quite as large for fine tuning. You can do just as well or sometimes better by training this smaller representation. Okay, so we're going to set up LoRa later down. First, we're going to enable gradient checkpointing. This reduces VRAM requirements. It's not absolutely essential. I like to have a function to define the trainable parameters. This lets me see a list of the modules in the model. Here I'm going to set up the LoRa configuration. So you remember I said we're not going to train everything. We're only going to train certain modules. The modules we're going to train are the attention, and we're also going to train the linear layers. So we're actually kind of covering most of the model. If you look at these other things like the layer norms, or you look at some other norms, these are actually a much smaller number of parameters. So we're kind of training most of the parameters in the model. However, as I said, we're training a much smaller adapter version of those parameters. So actually the percentage or the number of parameters we're training is much, much smaller than the model size. In fact, when I run this here, you can see there are approximately 20 million trainable parameters. And of all parameters, there's of course about 7 billion because it's a 7 billion model, and we're only going to train about 0.3%. Okay, next. So once we've set up the LoRa, which is the adapter we're going to train, we're going to prepare the data set, and we will load trellis function calling v3. Notice that previously I would have used function calling extended, but that's now deprecated. So we'll print out the data, which has the train, the validation, and the test set. And you can see it has the 3 columns: function list, user prompt, and assistant response. Next up, we're going to do some setup. So we're going to set up the prompts. We have these 3 columns of data from the data set, and we need to put those columns into a single line, a single prompt for each row that we're going to feed into the model. So here you can see that before the function list, we'll say you've access to the following functions, use them if required. And we're going to also set up the appropriate start and end tokens for this model. Now, the start and end tokens are usually specific to the model, which is annoying because it means you need to use different templating for every model. And we'll talk about that more when we get to inference. But for now, we're going to use the appropriate one for OpenChat. You can see if we were using Llama 2 or Mistral, we would instead use inst, end inst. If we're using DeepSeek Coder, we would use this. If we're using Yi, we would use this. But we're using OpenChat, so we're going to use this. So here's where we assemble the prompt, and you can see that basically assembling it involves putting in the functions, putting in the user prompt, and then finishing off with the assistant response. Now, I do go into a little more detail around the attention masks and also the end of sequence tokens. That ends up being important for getting good performance on these fine tunings. You need to make sure that you are penalizing the model based on the tokens that are being produced in the response. That's a little bit better than penalizing it based on how well it's predicting both the tokens in the prompt itself and the response. So for that, I'll direct you to another video I'll link down below. Okay, so our data set is now loaded, and I like to generate then a sample of that data set. So I set up a generate function that will just generate samples. And let's see what that looks like. So here you can see the whole prompt together, GPT-4 correct user. It's such a weird way to start off prompting on the user side, but that's what OpenChat does. You've access to the following functions, use them if required. You have 2 functions, the get big stocks and get stock price. And then we have the prompt request, which is get the names of the 5 largest stocks by market cap. And then the OpenChat model requires you to finish each turn with this end of turn token. And then we have GPT-4 correct assistant. So all of this prompt gets fed into the language model, and we then get it to generate a response, which we would like to be a function. And here you can see what happens if you use a model that's not fine-tuned. You can see it responds to say, to get the names of the 5 largest stocks, you can use get big stocks with the following parameters. So, I mean, the response is sensible, but it's not providing a structured JSON object. So this is not helpful if we want to easily connect to an API. And the correct response would be this. This is ideally what we would like. We would actually like this with an end of sequence token following here, which actually we'll see later. So we run 7 tests, and you can see for all 7 of these tests that there aren't clean function calls because the model is not fine-tuned. So let's move on past these 7 quick tests, which are purposefully for manual inspection. We'll move on to training here, and we're going to set up the trainer. And I will go through 1 or 2 of the parameters in the trainer itself. So we're going to pass in the train data set, and then for evaluation, we'll pass in the validation data set. And we're just going to train for 1 epoch. I like only showing the data once because it means that you're less likely to overfit. For supervised or unsupervised fine-tuning, you often pass the data through many times, but for function calling, because what you're really training is structure rather than the specifics of the content, I prefer to give more data to convey more structure rather than just giving the same data, because that's encouraging the model to repeat the exact same words. Okay, so we're going to train for 1 epoch, so the model should see the data once. By the way, sometimes you'll find it does a bit better for 2 epochs or maybe 3, but I find stronger models, they only need 1 epoch of training. The batch size, you could actually increase the batch size here, but the data set is quite small, so this is not going to be a long training. But you could increase the batch size. It takes up more space, more VRAM on your GPU. We've plenty of space on the GPU because it's 48, and the model itself in BF16 will be about 13. So we could easily increase the batch size here, especially because the batches are short. So each batch, every batch is just taking up KV cache. So every model is 13 billion, and then you have the KV cache for every batch. So the batch KV cache is going to be really small for the attention. So you really could have quite a lot of batches. I would bet you could probably run with a batch size of 16 if you wanted, or 32. Anyway, it's not a long training, so I just set it to 1. Technically, this allows you better granularity as well in the training. It means that the model will pick up more individual nuance. So I think probably batch size small is good if you are not constrained by time. Gradient accumulation. This can help if you have kind of wild, jumpy results. It will smooth because instead of back propagating after every batch, it will back propagate after every X batches. So here, I'm not going to use gradient accumulation. I don't see any instability issues, so this is fine. Okay, we're using a learning rate of 1e-4, and the learning rate scheduler type is constant. So we're going to have a constant learning rate. Typically in big training runs, you reduce the learning rate because as the model converges, you can't take as large steps in your optimization. But I'm going to leave it constant because it's a short training run and we're only doing 1 epoch. Okay, and then we'll run the training, and you can see here the training losses are pretty low, and the validation loss, it goes down 82, 79, 73, and then up a little 76. So what I do here is I just check that the validation loss is falling. It's going up a little bit here. That's probably okay. If you see the validation loss starting to go up a lot, then probably you've overtrained. And so I would recommend reducing the epochs. But since we've only got the epoch of 1, this is fine. If you were going to train multiple epochs, like 3 epochs, and you see the validation loss go up, then probably you should reduce the number of epochs. And here we'll go to an example after fine-tuning, so you should see the difference. So now we'll have the very same question, get the names of the 5 largest stocks by market cap. And indeed, we get the exact response we want, and we get this end of turn token. It's very important the model emits this end of turn token because it looks different for different models, but you need to know when the model is stopping generating, because otherwise it might generate the function and keep blabbing on, and you've no way to know then to stop the generation. So this token is very useful and important. And you can look at the other examples as well. The model does very well, actually. I think this model gets maybe 6 out of 7 of them exactly correct. The OpenChat model is quite strong. I recommend it. It's probably the best function calling model of the 7B that I've trained so far. I will just show you one little hiccup, let's say. And this can be expected, particularly with smaller models. So here we just prompt the model with some functions and then the word shop, which that's a weird prompt for the model. It's not going to have a lot of data that makes a lot of sense of that. And it does indeed respond with a function here, which is probably not the best response. I would have preferred it to say, what would you like to know about shops? So this is one place where it trips up. And then you can see I just have a generic test question about the planets in our solar system. And this is to test that it doesn't call a function when it doesn't need to. And you can see it does well here. It's got the same content of response as the answer that I would have liked. Now, just a few comments. Once the model is trained, you want to push it to Hub, or you probably want to save it somewhere. So I'm just going to show you how to push it to Hub. You've got the base model name. You want to define an adapter model. Remember, we've actually trained the adapter. We've frozen the model. So we're going to need to merge the adapter and then push to Hub. So I've defined the adapter model name. I've defined a new model name, and you can see those here. And next, we're going to save the model and push it to Hub. Now, when we just save and push to Hub, we're saving the adapter and we're pushing the adapter. So we still need to merge, which is why we call merge and unload. So we merge, basically we'll expand this adapter and merge it on to the main model. And then when we push to Hub, it will push the full model. Next, then you can save the pre-trained model, and you can also save the tokenizer and push the tokenizer. I'm actually going to skip down and show you that right here. So working backwards, we should have some code here. Let's see. For pushing the tokenizer. So here we save the tokenizer and here we push it to Hub. Now, the reason I do that at the bottom, I won't go into this in too much detail, but the reason I do that is because I first want to adjust the chat template. So if you look at a tokenizer object, I think I do it up here. If you print out tokenizer.chat template, it's going to print out this here, which is templating language. I think it might be handlebars or something. And what this does is it takes in a list of messages and it puts them in the format that this language model expects. That's why you can see that it has things like GPT-4 correct, which is the format for OpenChat, and it has this end of turn token, which is specific to OpenChat. But because we now need to not just have user and assistant messages, we also need a function message. It's ideal if we can also update that chat format to include function metadata handling. So basically, if I give a list with function metadata, user, assistant, it's going to format all of that into the prompt that I want. So here what I'm doing is I'm just setting up some functions and some sample messages. You can see sample messages here include a function metadata message, a user message. I've even just for testing included a function call message, a function response message. And then what I'm doing is setting up a chat template that's going to do well for this model. And then I'm going to apply that chat template. I'm going to apply it to my series of messages and see if the formatting is correct. So here you can see I've applied the chat template. So remember, we've got this discussion here. What's the current weather in London? And I wanted to format this into a prompt. So indeed, it's formatting it. It's putting in the start token. It's putting in the beginning of sequence token. It's then putting in the functions. It's then putting in my prompt. It's then putting in the first function call. And then it's putting in this little snippet here that's quite important, actually. So once you get a function call, once you call that function and get the response back, in addition to giving the language model the response, you want to kind of guide the model to use that response in a helpful way. And that's why I include here, here is the response to the function call. If helpful, use it to respond to my question request. And yeah, I think I've just realized if you're watching the Spanish part of the video later on, this is not yet updated in my Spanish video, this English language here. And I think actually that would improve the performance a little bit. So just keep a note of that. I didn't translate that little snippet. But anyway, it's important for the handling of the function call response, because once the language model receives this, up until this point here, the model will respond and say, that's great. Now say hello, end of turn. So once we've fed in everything up to this point here, the model then, when it gives a response, it's going to respond, taking the useful information from the function and using it to answer. So here it's answering the current weather in London is cloudy with temperature of 15 degrees C. And that looks good. And I've just manually appended on another request, which is saying, just for the model to say hello. So if I take all of this formatted prompt and send it in, the model indeed does respond with hello. Okay, just before we wrap up on this training script here, I just want to make a few quick comments because I get a lot of questions on pushing models to hub. So if you're merging the adapters, it will work fine if you're not quantizing. However, if you are quantizing the model, now what you have is you have a quantized big model and you have an adapter, and you're still training the adapter, but your base model is quantized. And unfortunately, it's not possible, although there's work being done on it, it's not possible right now to merge an adapter with a quantized model. So what that forces you to do is, instead of running this merge step here, which is not going to work, you actually first need to reload a base model, and you need to reload the base model in unquantized form. So rather than loading it with quantized precision, let's see if I can just show that here. Rather than loading it with bits and bytes quantization or some other quantization, you're going to load it in float 16, which is a 16-bit format, and then merge that model, merge the adapter onto that model. Now, there are slight inaccuracy reasons. For that, it will affect your precision, your perplexity a tiny bit. But broadly speaking, I found this still works if you're using a quantized model. So just don't forget, you need to reload your base model. Then you need to apply the adapter to that reloaded model, and only then are you able to merge if you're using QLoRa. Now, just before I move off of this run pod, I'll just show you, I often run a GGUF quantization. This allows you to run with Llama CPP if you want to run on a Mac. GGUF is quite a quick quantization. It's not data dependent, so you don't have to load data. It's much quicker to quantize than other forms. So there's a script here that will allow you to just run through. There's some installations. You need to install Llama CPP itself, and then it will go through and quantize. And by the end, you should be in a position to be able to push the model, which in this script here was Mistral, in GGUF form to the hub. And I'll just show you that if you want that GGUF model, I've created it for most models except for DeepSeek because I'm missing a file there, the tokenizer.model. But for the others, if you go to files, and if you go to the GGUF branch, you'll be able to find the GGUF file there. The nice thing is it's quite a lot smaller. It's about a quarter the size, maybe a third the size of the model in the BF16 precision. Okay, let's take a step back at where we are. We've gone through what a function model is, function calling model is with the Llama 2 example. I've walked you through the dataset. The latest one is V3. I've then walked through in detail fine-tuning a language model for function calling, including a brief section on GGUF quantization. So next up, we're going to focus on inferencing, and I'll take you through a very quick OpenAI function calling inference example, and then I'll go through Llama 2, OpenChat, and DeepSeek. So let's head back over to Trellis.com function calling, and you can see that there are inferencing scripts available. I mentioned earlier there are fine-tuning scripts, but these are inferencing scripts if you just want to get started quickly with making calls to a model that supports function calling. You can buy the script itself, or you can buy it as part of the Advanced Inference repo, which also has inferencing for long context models, for setting up a server on AWS, and also for using RunPod one-click templates. So we're going to head over to that repo right now, and here we are. We're in the Advanced Inference repo. I've just done git clone. I recommend that you cd into the function, the API call section, and you'll then want to create a virtual environment. There's a description in the README of how to do that. I've called it API env. You want to activate that, and then you want to install some packages. I'll just show you the README here. So rather it's this README here specifically for API calls. So as you've git cloned the repo, cd into the repo, set up the virtual environment, and then install these packages here. If you're going to use the OpenAI function calling, you'll also want to install TickToken and OpenAI. And if you're going to use a Yi model, then you want to install sentence piece, which is needed for the tokenizer. Next, you'll want to go to the environment variables and you want to set your OpenAI key. I've created a sample.env file, so you can simply copy this file and rename it .env. And in the .env file, you'll put in your OpenAPI key. And then for running RunPod, you'll put in the pod ID and the model, but I'll show you that a little bit later. So let's go back to the README here. Once you're in the API calls folder, you then have the option to do some simple API calls to OpenAI or to RunPod, which is where you'll run a custom model, or you can do what we're going to focus on today, which is the function API calls for calling functions. So let me just CD into function API calls. In fact, I'm already there. You can see if I do ls, I've listed out the files, functions, and actually I'm on the ESPANOL branch. So I'm going to do git switch and get to the main branch. So this repo has got two branches right now. If I do git branch, there's the main branch, and then there's a Spanish branch, which I'll talk about a little later in this video. So on the main branch, if I do ls, I'm now in this function API folder, and I have a few scripts. The first one I'm going to look at is OpenAI function call.py, which is going to allow me to run OpenAI function calls. Now, the basic setup you need for doing function calling with a model is, first of all, you need a model, and second of all, you need functions. You need to define those functions. And those functions are defined in the functions folder underneath tools. So in tools, what you have is a list of information that you will provide the model within the prompt. Here I've got get current weather and a description of the parameters that accepts. And I've got get close, which is a function that when given the weather conditions, it will get me the clothes to wear. So for example, if I call get current weather for Dublin, it will say that it's cloudy. And then if I call get clothes with it being cloudy, it will say to bring maybe a raincoat. So you can see these functions, I've set them up in a way that function call chaining is possible. That would be a case where you want the model to first off call for the weather. And then once it's got the weather, the model should call to get the clothes appropriate to wear for that weather. So this is called tools.json. It's the same file that you will fill out for calling OpenAI, but it's also the same file you'd fill out, at least as I've set it up, for calling any of the custom models. Now, this is the data that goes into the models as function metadata, but you also need to define individual functions, which I've done here, and they each have their own file. So I have a get close file, which is a function that takes in temperature and condition, and then it will output the outfit that you should wear. And I have get current weather, which takes in a city and optionally takes in either Celsius or Fahrenheit, and it will return the weather data for that city, or it will say there's no data available for that specific city. So you need to set up your two functions here like this. Now, once this is done, you can go to the OpenAI func call.py and you can set the model that you want. I'm just going to use GPT 3.5 Turbo. And this supports function calling. I believe GPT 3.5 Turbo without this date at the end will also support function calling. And what's happening in this script is it's going to import my list of metadata for the functions. It will also import the functions themselves. And when making a chat completion request, it's going to feed in that list of functions via tools. So tools is my list of function metadata, and it's going to feed it into the chat completion request. And when the data comes back out, I'm going to have a function ready here called execute function call. So when I do a chat completion request, it will return a response, and then it's going to allow me to call execute function call. Here I have a function that will just print out the messages that I've submitted. And here I set up a chat. So I'm going to start by creating a messages array, just that's empty. And I'm going to add in a first message that says, what's 1 + 1? And then I'll get a completion request. And when I get a completion request, I'll have an assistant message. And I'll check if that assistant message is a function call. And if it is a function call, then I will execute a function call. And if I execute a function call, then I'm going to send the data I get from the function call back into the language model. and get a second chat response. So basically the model says, I want to know the weather. If I get the weather, I give it back to the model, and then the model will respond so it can synthesize and respond with that data. And then we'll have a response at the end. Now here I've just asked what's 1 plus 1. So I don't expect any function call for this first simple example. So let's just try that out. Python, OpenAI func call.py. And let's see if this works. Okay, so 1 plus 1 is equal to 2. Now we'll move on and we'll ask what's the weather in London. So here we should expect a function call in this case. Okay, so what's the weather in Dublin? The assistant message is actually none in this case because OpenAI considers that it's a function call response. But there is a function call, which is temperature and cloudy. And given that information, which is fed back to the model, the assistant will respond, the weather in London today is cloudy with a temperature of 15 degrees. So that is working well, and it's made use of my function call. So let's try a little bit more tricky question, which is, what clothes should I wear? What clothes should I wear? Let's just say I'm in Dublin. So let's see what it does. So here, it should ideally ask first for the weather, and then it should ask for clothes. So indeed, it does call to ask for the weather. And that makes sense because if it asks for the weather, then I'm going to be able to feed that back in to the model, and then the model will be able to ask for what clothes to wear. So this is a very simple example. I actually build on this for the custom models, and I'll automate that chaining so that it will automatically call the model, and it will keep on calling functions as much as it needs, and then stop and provide a final summary response back. So this is a quick summary of OpenAI, and the reason I wanted to show it to you is because you're going to use the exact same format for formatting your functions, and you're going to use the exact same functions when you use the custom models that we're going to run through RunPod. Next up, I'm going to show you how to query models like Llama 2, fine-tuned for function calling, then OpenChat, and we'll finish off then showing you a DeepSeek model, which is a 67 billion model, and I'll also show you that model in Spanish as well. So let's go over to the model card. We can check out Llama here, and just go to the model card and scroll down for the RunPod template. So what we want to do is get started quickly here, and I'm going to open up RunPod template, which is one click. And this is going to allow us to set up a server very quickly that we can then do inferencing on with function calling. Okay, so we have the template here, and I'm going to pick a GPU. I'm going to pick the A6000 again. I'm going to click continue and deploy. Now I'll be able to grab the pod ID here. This is running still from the fine tuning I was showing you. So I'm just going to close that pod down so that I'm not spending money on it. And then I will delete that pod as well. And now copy the ID of this Llama 2 pod and head over to my .env and update here to Llama 7b. And here I need to put in the model ID. It's the model slug from Hugging Face. Actually, I can get it just by copying there and saving. So this sets up the pod. It means that we're going to be hitting this endpoint of RunPod, running text generation inference. And we're going to be using this model. It's important to specify this model because that is going to define the chat template that we're going to use. And where we're going to use it is in this RunPod TGI func call chat template script, which is going to allow us to inference the function calling model. And you can see here that we're importing the pod ID and we're importing the model. The pod ID is needed because that gives us the URL that we're going to hit. Actually, this is the URL that we hit for generating responses with TGI, and the pod ID is inserted right in there. So the pod is going to take a few seconds to initialize. If we go over and check out the logs, we can see here that the system is extracting. It'll take a minute or two, and then the shards will download and the model will start to run. Now, before I start inferencing that, I'm actually going to start up a second pod. And the second pod that I want to start is going to be the OpenChat pod, just so we have that running in parallel. So I'll just search for OpenChat Trellis v3. And if I scroll down on that model card, I should also be able to see a one-click link. I think I've gone too far. Yeah, here we go. So there's my one-click link. Now, importantly, when I use this template, I need to specify a token, an access token, because it's a gated repo, because this model is available for purchase. So let's check out this function calling model with the A6000. But when we customize the deployment, we're going to add in here another variable, which is Hugging Face Hub token. And then I'm going to go to my settings and I'm going to get a token. So I'll scroll down to access tokens. And I'm going to use the one I use for RunPod. Read permissions is enough in this case. And I'll copy it in here and click set overrides and continue. So this now should be running two different pods, both of which are starting up. I'll go back to my pods here. Let's take a look at how things are going with, yeah, it's still initiating. So we'll give that a few minutes and the other pod should be starting too. Of course, when we start to use the OpenChat one, we'll have to swap the pod ID on our script in the .env file. Okay, so just as a brief overview of what happens in this script, first off, we download the tokenizer for this model. That's why we have to specify the model. And the reason for this is to use the apply chat template. Apply chat template will format a list of messages automatically into a long prompt. Of course, for OpenAI, you just send the messages, and behind the scenes, OpenAI decides how to format the prompt. We don't see that. But because we're calling a custom model here, we do need to properly format that prompt. And that's why we need a tokenizer. And that's why later on down here, I can just show you once we go to the chat completion request. One of the first steps we do is tokenizer apply chat template and get the formatted messages. Okay, so we are, just like OpenAI, we're importing our list of tools. It's the same list of tools. It's just the function metadata. Then we import our functions. Again, the same functions, get close, get current weather. Then we define executing the function call. That's the same as the OpenAI. We are just going to call the function when the model asks for us to call the function. I have a short function here to test the API is up. Just checks that the pod is running and will give you an error if it's not. Then we have the chat completion request, but this time using RunPod. It will first off check that the API is up and running. And next we have a recursion depth check. So you'll remember there was a case where I said we would call two functions. So first we get the weather, then we get the close. So that's a chain of calls. And you can have like multiple calls if the language model is strong enough. But what I want to do is limit an infinite loop. So I've got a counter and it's going to count how many times we have looped. And it will exit after, I think, 4. Max recursion depth of 4. So basically this will stop us from chaining infinitely if there was a problem with the model. Next, we format the messages. Just to show you what the messages might look like, you set up a list of messages. The first one has to be the function metadata. Then you have user, and you keep appending in. You need to append in the data you get back from the function call. You need to append the data we get from the response. So this is your list, just a sample list of messages. I like to print the formatted messages so we can see just down here what that will look like. And then we have our curl command. So the curl command will make a call to RunPod and it will send in the payload. which includes the formatted messages. It also includes the max number of tokens to generate, and do sample equals false. Do sample equals false means that it uses greedy decoding. It means it picks the most likely next token every time. So it doesn't have any temperature. The temperature is 0. I like this parameter a lot because I think with temperature you will tend to get less consistent responses, and you want to have consistent responses for function calling. So once the curl command is set up, we will try to get a response, and once we get a response, we're going to extract the generated text. And once there's generated text, we're going to check if there's a function called JSON. So we'll try and load a JSON object, which would indicate a function call. And if there's no JSON object, then that means it's a normal response. So we just append the response as an assistant message into our list of messages. But if there is a function call and there's a function name specified, then we're going to append a function call. So we'll append that data in under the function call role. So there's a user role, an assistant role, a function call role. Then we'll call the function, and with the results of the function, we'll append a function response. So this is the function response role. And as I said earlier, if there's no function JSON, or if there's no name of a function in the JSON, then we're just going to append the response as an assistant message. Okay, just one last thing here I skipped over, but it's important. Once we do get the function response, we actually call the API again. This is actually a recursive function, so you can see we're calling the function that we're in. So we're in the chat completion request, but we're going to keep looping with more chat requests so long as functions are being called, and this allows us to get chaining. Here I've just set up printing, so it will print a nice conversation here to the screen. And next we'll start with our chat script. So first we have our messages, then we have to append the function metadata, which is simply the content of the tools file here. And we're not going to include a system message here. You can with some models have system messages. Llama supports it, Mistral supports it, Yi does not, DeepSeek does not. And then we will start to send in some messages. I'm going to send in a trivial one first. What is 1 + 1? But first, I need to check that we are up and running. And let's see here. So in the container logs, yep. So it looks like our Llama model is up and running. And we can check if OpenChat is up and running. Yeah, actually both models are up and running. So let's go across, and we're now going to be able to run this script here. So Python run pod. Sorry this is so long, but I wanted it to be descriptive because it's a run pod server running text generation inference for function calling specifically, and it uses chat templating. So you don't need to set up the prompt yourself because we use this tokenizer.apply chat template. Okay, so now calling with our simple question. Let's see what happens. Okay, there's 1 + 1. 1 + 1 is 2. That's good. And just to show you here exactly the prompt we're sending in, you have access to the following functions, so use them if required, the 2 functions, and then what is 1 + 1. So this is the exact prompt that goes in, and then this is the pretty formatting of the discussion. Okay, so that's our basic answer. Now let's try the next question, which is what is the current weather in London? What is the current weather in London? We expect the model is going to respond with a function call to get the weather for London. That's what we expect. So let's see if it does that. And it looks like it has requested the weather. And based on our information, based on the information, the temperature in London is 15 degrees and the condition is cloudy. So that's great. We're getting the right answer for the weather in London using one function call. And next, we're going to ask what clothes should I wear? I'm in Dublin. So here what should happen is the model should first realize it's in Dublin, get the weather for Dublin, and then figure out the clothes to wear in Dublin. So let's try this out. And remember, we're using a Llama model here. Just a small criticism of the Llama model, and you could maybe improve this by adjusting the prompt format. But if you look at that response we got, it does say the weather is 15 degrees, but it does include this little snippet we don't really want, which says, thank you for providing the response to the function call. So that's not ideal. Okay, so here, let's see exactly what it's doing. So actually what Llama here is doing is calling a function for getClose, and it's just hallucinating the temperature and the condition. And then the function response is working, and it's responding correctly based on the function response it has. So you can see some of the functionality is working, but the model is not strong enough here. It's basically hallucinating, unfortunately. So let's move to look at the OpenChat model and see if that's going to run a little bit better. What we need to do here is swap out our pod. I'm going to shut down this Llama function calling pod. Let's close it. Let's close it. Okay. And let's grab the pod ID from the OpenChat one. And we got to paste that in here. And we also need to grab, the OpenChat slug. So I'll just put in OpenChat Trails. So v4 is not here yet. OpenChat Trails v3. Let's see what we get. Okay. And here, I'm going to paste this in. Let's take a look. Okay, that's great. So let's go again and ask all the basic questions. We'll start with 1 plus 1. What is 1 plus 1? And the beauty here is that we just had to change the model and the pod, and everything else is automated within the script. So 1 plus 1 is 2. That is good news. And what's the current weather? So let's see how it handles this. Yeah, so this is better. It's better because it gives a clean response. It doesn't prelude it by saying thank you for this information. It just gives the response. So that's quite nice. And let's try the old tricky one. So here we would love if it called the weather first and then called getClose. Yeah. So this is a thing of beauty here. What clothes should I wear? I'm in Dublin. Function call getWeather. Then it actually gets the weather back and uses that to call getClose. And then it gets that response and it says you should wear a long sleeve shirt and jeans, which generally is good advice for Dublin, to be honest. So yeah, that's OpenChat. And you can see there the difference between OpenChat and Llama. Mistral, I think, is a bit better than Llama in my experience with these function calling. You can get the Mistral model. OpenChat, I think, is probably the best performance of what I've seen. So with those two models done, let's take a look at a much bigger model called DeepSeek. It's a 67 billion model. There's also a Yi 34B model, which is good if you want long context. Now, something I've seen, and I don't have enough data to say this for sure, but generally I find models that have been trained for coding do particularly well in function calling, which probably makes sense because there's a lot of JSON objects within coding. And what that means is that actually, if you wanted to do function calling with a coding model, it's going to perform well. Whereas if you move more towards a language model, and the Yi model seems to be more language than coding, it's not quite as strong. So even though Yi 34B is larger than OpenChat, I think in some cases it's a little bit worse for function calling. The problem, of course, is that for many applications where you're using function calling, it's not just a coding application, and therefore it's necessary to use a model that's for language like, say, Yi or like Llama or Mistral or OpenChat for the smaller ones. But what you probably couldn't use so well for maybe customer service is something like DeepSeek, Coder, or Code Llama. Those models are really good. The DeepSeek model is really good. DeepSeek Coder specifically, not plain DeepSeek, but the DeepSeek Coder model would not be as good with normal language. That would be important for your chats. Next up, I'm going to take a look at DeepSeek 67B, the function calling fine-tuned model. I've started up the one-click template, function calling DeepSeek 67B by Trellis. it's up and running. If I check the logs here, I can see that the server has started up, and this here indicates that it's ready to receive API calls. Now I've copied that ID of the pod, and I'll go over to my scripts. Here I'm in the advanced inference repo, and in my .env file, I've just pasted in the pod ID, and I've also put in the name of the function calling fine-tuned model right here. Okay, so next up, I'm just going to cd into the API calls folder, and I'm going to activate my virtual environment where I've installed the packages earlier. So I'm going to do source api env bin activate. And now that virtual environment is activated, I'm going to cd into the function API calls folder. Okay. So here I am in the function API calls folder, and I'm going to open up the runpod TGI func call chat template. This is the template that allows me to run function calling against the runpod API that I have set up. So we're going to start off with a basic prompt here using DeepSeek. Let's scroll down to the very bottom here to where I have the chat scripts. And you can see the user prompt is the most basic one, which says, what is the current weather in London? And you'll remember that we've given the model a function to get the weather for various cities. So when I call this, it should do a function call. So let's do Python runpod TGI func call chat template.py. And here we should see what's happening. It's going to call the API at least twice because it needs to make the function call, get the response, and then summarize it. So here we can see it's made a function call. And let's see what it's recommended. So here the chat starts off. Actually, I've run the second. I forgot to click save. So I'm actually running this prompt here. What should I wear in Dublin? So I'm asking, what clothes should I wear in Dublin? It makes a call to get the weather in Dublin, because to call the function for getting the clothes, it needs to know the weather. So it calls the function for getting the weather. Then it calls, it gets the weather. It then calls a function to get the clothes. And then it summarizes that function call, saying that you need to wear moderate clothing like a long sleeve shirt and jeans. So this is perfect function calling performance. DeepSeek is quite strong. It's a big model. So as you can see, makes a function call, gets the response, makes another function call and gets the response. That's a pretty advanced usage because the language model has to determine that it first needs to get the weather before it makes the function call. Okay, let's make that more basic function call here, just asking what's the current weather in London. I'll click save and head back. Notice that there were 3 calls to the API in the previous one because there were 2 function calls plus the summarizing call. So here we're just going to run and ask the weather in London. So what's the weather in London? Get current weather. It makes a function call. It gets the response here. And then it says the current weather in London is 15 degrees C and cloudy. So it gets this, which is not surprising because it's easier than the other function. And of course, I always like to have a very mundane test function that can be used. Just directly asking the LLM what is 1 plus 1, and it says that it's 2, which is correct. Just want to make sure it doesn't accidentally call the function. So this is the DeepSeek model. It's probably the strongest model that has function calling fine-tuning done, and it's available online on Trellis Smart, and you can find links more below just below the video. The next thing I want to show you, and I'll do it again with the DeepSeek model, is function calling EN ESPANOL. So I have a branch here that I'm just going to go to git branch to show me the branches. There's the main branch and there's the ESPANOL branch. So I'll do git switch ESPANOL. And I do have some changes I just need to discard. So let's discard those and git switch ESPANOL. So in addition to having functions available, we have functions now in Spanish. And I'll just very briefly show you this. I've translated, or rather ChatGPT has translated a function for getting the current weather. So, for example, una función simplificada ficticia para devolver datos meteorológicos de una ciudad. So it's very much the same. You'll notice that anything to do with coding is maintained in English, like def for defining the function, but everything else is translated into Spanish. Now, I've done the same here for obtener ropa. Apologies if there is bad Spanish here. My Spanish is mediocre and I rely just on GPT. So this will get you a set of clothes given la temperatura y la condición. And then the metadata, again, you'll see these, the keys are in English, but the values are, actually this here function is still function, but the rest is in Spanish. So I've translated everything to Spanish, and I've also made a little change to applying the chat template. You can see right up at the top here in the Spanish branch, in the Espanol branch. When I load the tokenizer, which is right here, I then actually adjust the chat template. And the reason I adjust it is because I want to put in this Spanish here. Tienes acceso a las siguientes funciones. Úsalas si es necesario. So I've changed that to Spanish as well. And this will basically allow me to do a fully Spanish chat. If you go down to the messages, the sample messages that I have. Okay, so we're going to start off with a basic question. I've got ¿Cuánto es uno más uno? So we should be expecting a text response here. And I've actually just run it, but let's run it again. ¿Cuánto es uno más uno? And uno más uno es igual a dos. So that's good. And the next one is ¿Cuál es el clima actual en Londres? So let's try this one. And let's see. Yep, nublado. We have a function call. And el clima actual en Londres es nublado y 15 grados Celsius. And just so you can see the function syntax here, here's the raw prompt being sent in. So the API has been up and running. And then here the prompt starts. So user, tienes acceso a las siguientes funciones, úsales si es necesario. Then it'll give the function descriptions in Spanish. And then it will say, ¿Cuál es el clima actual en Londres? And then assistant will call a function. And then the function response is called by my Python script. So it says, here's the response. If helpful, use it to respond to my question. Temperatura 15, condición nublado. And then the assistant has to respond to this. And the response that the assistant gives to that is, el clima actual en Londres es nublado y 15 grados. So this works quite well, and it works well for the basic functions. I'm going to show you one further example. So, ¿Qué ropa debería ponerme? Estoy en Dublín. So this is the harder example because we're asking what clothes to wear in Dublin, which requires the LLM to call first for the weather and then to call for what clothes to wear based on that weather. So let's run that function and see what happens. So first off, let's see if it does call a function, and it doesn't. So it says, para saber qué ropa deberías ponerte primero, necesito saber qué clima hace en Dublín. So it's saying to know what clothes to wear. First, you should know what the weather is in Dublin. Could you tell me what the weather is in Dublin? So this is a sensible response, but it's not quite as good as it could do because it should be able to call the function to get the weather automatically by itself. So a few things here. I guess possibly it's because the model is just not as strong in Spanish as it is in English. But something else is you could look at the functions themselves. For example, if I go to tools here, there definitely could be some improvements if you carefully write out these functions or even get help from ChatGPT to improve the quality of these functions, the clarity, making it really clear when the model should call them and what is required for a successful call. Just by improving the functions themselves, that can definitely improve the quality of the responses you get. But it's good to know that this DeepSeek model certainly provides pretty good responses in Spanish. And it's also useful to know that if you just translate the function call and you translate all of the data, you can get pretty good performance in other languages. And that's it, folks, for the big overview of function calling. You can get a lot more information on Trellis.com, particularly if you go to the function calling section where I've linked the datasets, the inferencing, and also the training. Just a few thoughts before I leave on which models to choose. As you know, as you move to larger models, they are more accurate, and the larger models are generally better at function calling as well. So if you need precision, or particularly you need chaining, or you need to have strong logic from the model within your function calling application, it's going to be better to use larger models. As you saw in this video, OpenChat seems to perform the best of the function calling models compared to Llama. I didn't show it, but it also performs a bit better than Mistral and seems to be able to do function calling chaining in certain cases. Of the larger models, the DeepSeek model is probably the best at function calling applications and seems to perform similarly or better than the OpenChat 3.5. Of course, that would be partly expected given the model size. Now, function calling syntax. Exactly what symbols and prompts you put where is really important to get good performance from function calling. Little differences like having a few extra lines or an extra character or having a beginning of sequence token where it shouldn't be there. Small differences like that can really affect the model in producing JSON objects. So you need to be really careful with the templating. And that's why when I was building V3 of the function calling dataset and models, I wanted to release as well an inferencing repository to try and make it systematic how the prompt is generated. And that's something, as I showed, can be done using the apply chat template portion of the tokenizer. That's pretty much it for this video. Let me know any questions below. If there are any extra models that you think would be useful to fine tune, let me know the application and what the model name is, and I'll see what I can do. Looking forward to chatting more, folks. Cheers.